Thank you, Janine. So I've been on this campus for almost 20 years, and one of the things that continues to impress me is the degree of talent that we have squirreled away in different corners of both campuses. And our next speaker is a great example of that. Her work is not necessarily directly related to invasive species, but we're working very hard to begin to entice her to work in this space. And I think after you hear her presentation, you will hear why. So, I'm very pleased to introduce Dr. Atena Haghighattalab. She is the Phenomics lead in CFANS within the Stakman Borlaug Center. She is very skilled at remote sensing, GIS, high-throughput phenotyping, and big data analysis. Her work entails identifying current and potential University of Minnesota research capacities in the area of high-throughput plant phenotyping, including engineering, the plant sciences, and informatics. Her research is supported by a partnership with PepsiCo. So Atena, I'm very happy to hear from you.
Thanks for the introduction. I was impressed. I thought you were introducing somebody else. Like, who is this person? Thank you. Thanks for the invitation and this opportunity. And thanks for pronouncing my family name this way. I was impressed for that too. I want to say 1 minute about my family name. It's very hard to pronounce, and it's Haghighattalab. And I was 5 years old when my dad actually changed our family name. And our family name was Nili, N-I-L-I. It's beautiful. It means when the blue color of ocean meets the blue color of a sky. Who changes that? And then I was 5 years old, my dad walks in and he goes, oh, we're changing this family name to this, Haghighattalab, which I'm from Iran, which even in Farsi, it's a sentence. It's not even a name. And it means I want the truth. And I was 5. If I was older, I would be like, dude, people get that tattooed. They don't change their family name. But that's what he did. Anyway, yeah, I want to, so I don't have academic background in agriculture. My degree was in remote sensing engineering before civil engineering, and I got into the area of agriculture through working for Coors Brother, the beer company, and then after that I worked for Jesse Poland's lab at Kansas State University, and then I worked at Summit in Mexico, and that was my journey through plant pathology and agriculture and precision agriculture, and now I'm here. So I want to talk about application of drones for breeding nurseries. So most of my work was in wheat, sorghum. I worked for strawberries and potatoes and other things, but I want to start with this slide that talks about the challenge the challenge that we're facing in agriculture. This slide shows the project. It's from 1960 to 2050, and it's the demand versus the production for wheat, but it's the same for other crops. So either the first line, the green line, shows that based on the current knowledge that we have. Let's look at the orange line. The current trends, based on the current knowledge that we have, it's not bad. The red one, if you believe in climate change, it's going down. But we need to increase, if we believe that we have climate change, the population will increase, and all these things, then we know that we need to increase the yield for major crops, yield corn, soybeans, sorghum, and all of these things. So this slide just shows that to move forward in the future in agriculture, we need to find ways to adapt agriculture, to adapt our crops for stress, for lack of nutrition, for lack of water. And to find a way to do that, we need to use technology. So this shows that in the plant breeding, this is based on my knowledge in plant breeding. So if there is plant breeder here, ignore me. So based on my knowledge in plant breeding is a number game. This is what I get from plant breeding at Kansas State University. It seems like plant breeding starts from like a big number, a bulk population. So they start with planting, for example, in a small breeding program with like 300,000 plants. They start with that, and then they plant it in the field, and they have to choose the best ones the first few years, and then it goes down. They have small plot yield test. They do the test, and they come down to 3,000 plots, and then it goes down, down, down. They have advanced trials, and then till 10, 12, up to 15 years later, till they find the best. For example, if this is for wheat, the best wheat variety that was better than the one before. It has higher yield, better quality, the height that they want. So it takes 15 years to release a variety. 10, 12 to 15 years. That to me, it's a very long time to release one wheat variety. So every time you go and see a new bread or a new pasta, just think about that. It took this many years to release that specific variety. So it comes to this point that we need to cut this time and make it faster, and also make it more precise. But how can we do that? So we need to, the process of making this faster, it's called high-throughput phenotyping. What is phenotyping? Phenotyping basically, as I said, like, okay, so it starts with like a bulk population, and then they go through the field, and they look at different variety, and they say, okay, this one looks healthier, this one has the right height that we want, this one doesn't seem, this one is like more resistant to the diseases. So it's all the characteristics that they want. It's all those physical characteristics is phenotyping. High throughput phenotyping is determining those characteristics in a faster way. But what does high throughput phenotyping to us means? To us doesn't mean that if we do it in the field faster, because yes, we can use the satellite imagery to do it faster. We can fly small airplanes, Cessnas, and do it faster. We can use drones and do the process faster. So that's that one part in the field, that's high throughput phenotyping. But what if we do that part faster and then bring all those bazillion data points to the lab and then have the grad student or an undergrad or postdoc and be like, okay, now sit here and analyze this data for weeks. Then that's not high throughput phenotyping, because we just moved the part from the field to the part to the lab. So for us, high throughput phenotyping means high-throughput phenotyping both in the fields and also automated or semi-automated platforms that we can do it also in the lab, yes, using the computers, machine learnings. So decrease the burden in the field and also increase the efficiency of the program in the lab also. So this is a good example, because when I was in Summit in Mexico, I would see that this is how they would measure the height of the plant. They had this roller, and actually this was more advanced way, because otherwise they had just this roller that had measurements on it, and then visually they would see what's the number, and they would write down the number. But this was more automatic, and they would just like tag the number. So they would just run, technicians would run, well, so it's technician-based, the number, so human error. They would just put the roller in the middle of the field, in the middle of the wheat plot, and then visually measure the height and just move to thousands of plots, and it's Summit, Mexico. It's huge. But if you use, for example, satellite images, or if you use fly Cessnas, take any 3D models, or if you use drones, we can create a 3D model, which I will show you later, and then measure heights. That way there is no human error, labor time, and the accuracy is obviously way higher. Well, this is one of my favorite. It says, necessity is the mother of invention. I agree, but I'm a lazy person, and I think laziness is the father, and that's why if you're lazy, you come to automation, and you want to like automate the whole process so you don't have to do it in the lab over and over. So why do we use drones and not other technology? This is an amazing technology that I work with, what does this do? It's a tractor, and it has it can carry all kinds of technology on it. It has you can put green seeker that measures different vegetation indices, NDVI. You can put canopy temperatures on both axes of it. You can put sonar that measures plant height, and imagine plant height that from like 1 meter or 2 meters off the ground. So the resolution is very high. It measures RTK, the exact location of the plant, and the accuracy level is centimeter. It can carry multiple cameras, RGB camera, so the weight is not a question. So you can put RGB camera, hyperspectral camera, multispectral camera, anything you want. So the pro is that lots of equipment, it's flexible deployment, and easy to operate. I can run it, so anybody can run it, right? But what's wrong with it? It costs a lot of money, and I'm somebody that likes to have open sources, likes to tell, for example, a country like Pakistan and Bangladesh, hey, this is a technology, I want you to use it. But there's no way that any other developing country, or even so many states and university here, public university, they can't be able to purchase this. So it's very expensive, and it's not completely automated because all of these sensors, they can't be simultaneously work together and give you the data. And another important thing is, so imagine, yes, you get the canopy temperature. So you start running this machine, and you start running it here. You measure the temperature at the plot number 1, and machine runs, goes to plot number 100. All the environment effects changes. So by the time you're at the plot number 1, the temperature is X. But by the time you get to plot number 100, all the environment changes, the wind, the temperature, so all of these changes. So it's really, the temperature that you get, it's continuously is changing. So how can you really calibrate all these data? So that's another problem with these machines. So I'm showing all of these to justify why we're using drones. This is amazing technology. So it just shows you that we also developed this software at Kansas State University to collect all these data. But at the end, it comes to the fact that drones are cost effective. You can buy a drone, IRIS drone is like $700, and it goes all the way to thousands of dollars. Depends on what kind of sensor you want to put on your drone. If you want to put an RGB, you can go with a 700 drone. But if you want to put a heavier platform or sensor, then you have to go higher. It's very fast. Depending again, what is the weight of your sensor. You can fly your field, a 3 hectares field, like in 10 minutes, 12 minutes. It can be equipped again with several, not like that tractor obviously, but again you can put RTK GPS on your drone, you can have a RGB camera, and you can have probably a multispectral attached to it or a thermal attached to it. Very high resolution, remotely sensed data again. You can fly 30 meters above the ground and get very high resolution data versus, not versus the tractor, but versus flying Cessna, small airplanes, and obviously versus satellite imagery. and temporal resolution. So imagine if you use satellite imagery, satellites usually collect data every 14 and plus. But with drones, you can fly today, and you want to fly next week. It's rainy, it's windy. Okay, you fly the next day. So the temporal resolution, it's very high because you can fly almost any day that you want based on the environmental effect and the changes. And there's so many different drones. The one, the light blue one is a $700 drone, and if you crash at any part of it is like less than $10 cost, and you can buy it on eBay. The big one here, we built it at Kansas State University, and it doesn't work. And I hope that doesn't go on YouTube. And then the big one on the back, the black one, that's a $1,000 drone. So this one just shows different ranges of the drones. And in front, it's just different kinds of sensors and cameras with different prices. And the one on the right, this one collects video imagery, and I'll show you an example of that one. So there are different options based on what is their application and what kind of sensor you want to put on it, and what is the resolution you want to have, if you want to do forestry, if you want to do precision agriculture, if you're interested in river, or if you're interested in plant breeding, what we work. So for example, this one, it's a DJI Matrix 100. We put Mycosense Redditch is very popular if you work in plant pathology, plant breeding. And I think Mycosense Redditch, Mycosense Redditch is blue, red, green, and it has the Redditch, which is between red and near infrared. And I think it's about, if I'm not wrong, $5,000 to $8,000. Then you can just like, what it has is that there are so many companies that you buy the drone and you buy your sensor and they create the rest for you. But what we do is that we customize the rest ourselves. We customize, there's part that gimbal that attaches the drone to the camera. And what it does, it makes sure that your camera doesn't move around, and it always makes sure that it has a nadir view to the field. And so the rest that the technician in the lab, they can customize the rest. So what are the applications in the field? And I worked on these. For example, one of them, very easy, but so many farmers either don't know about it or, but this one is really easy and it's very interesting to me. It's weed management. So I don't know about Minnesota, but in Kansas, Canada thistle, if you have it, it's the same here. If you have it in the field, you have to legally remove it. So this is a picture of Canada thistle in the field. So we flew this too late for the farmer, but we only flew it just to show him that we could have done it for you. But I'm going to show it what happened at the end. So this was a cornfield in northwest Kansas, and the red dots are what we were able to classify after taking the drone imagery as Canada thistle in the field. So the farmer had to, because we did it too late, he had to do the whole field, herbicide the whole field. And it cost him, he did a single rate treatment for $3,900. But after we did classification, we flew the drone half a day or less, not even half a day, it was like maybe 31 hour, 120 acre. And we found that only 0.6 acre was affected of this 120 acre. And he could have only spent $500 versus almost $4,000. So that would have saved him $3,400 on these weed treatments. For a simple, not very simple, Canada thistle is important, but for this simple weed treatment. So this is a very simple herbicide application using drones. It's out there, drone is out there, and this is something that happens every day, and it's an application of drones. Another thing that we did a lot of times in Iowa was for crop insurance companies. Farmers and insurance companies always in fights because they say, okay, hail damage is not in the insurance, or this disease is not insurance, but it's very easy to fly a drone and detect using machine learning and automation systems say that, okay, classify the image, look at the images after taking the drone imagery and say, is this disease, or was this only hail damage? Was this water deficiency, or was this something else? So using remote sensing techniques and using machine learning techniques, we just can say that this was a hail damage, was it in the insurance, or was it not, and just solve the fight between the farmers and insurance companies. So now back to what we do for plant breeding. So, as I said, I don't have background and knowledge in agriculture, but what we do for plant breeding is not limited to plant breeding. Phenotyping or high-throughput phenotyping is really a multidisciplinary area, and what we're trying to do is that bring all different disciplines together. We want to have engineering, bioinformatics people, obviously plant breeders and genetics and physiologist people together. Why? Because when we have plants and when agriculture is involved, genetics, they have to look at the gene level and tell us what is about these plants. Physiologists, they tell us about the environment and how these plants look and how they are supposed to look in the environment, in the field. Engineers, they help us to develop either if it's robotic machines in the field that we want, if it's drones, if it's sensors, they are the ones that need to help us with developing the platform. Bioinformatics, remote sensing, GIS, geographers, they need to help us with analyzing the data. So it goes from genes to physiology, to developing the platform, and also to help us to automation and analyzing the data in the lab. So that's what we're trying to do in our center here. And to do this, there is a lot of, so it's not just like flying, getting the drone, buying the sensor and flying the drone. There's so many preparation. Before you fly the drone, you need to know that, okay, I have the calibration step. I need to have in my field some ground control points, because if I fly today and if I want to fly next week, I need to have some base comparison between today's data and next week data and next month's data and maybe next year data, because I want to compare my next year data to previous year. So there are all these knowledge that you need to collaborate with someone from remote sensing department, with someone from geography department, with someone from computer science department, and that's what we're trying to do. So these, this one shows like, oh, that's Carlos. Carlos, all we could talk about in Spanish was about my cat. His name is Freddie Perkery. He's amazing, and Carlos really liked him. So, so these are the things that we try to tell scientists or our collaborators to acknowledge that just because you're working with drones and just because you're working in this area and buying a drone, that's enough. It's not. You really need to collaborate with other people and try to get their expertise and knowledge. So this is one of the things that I worked and developed. This shows that, okay, we have all the data, and now let's do automation. This is an automated pipeline for image processing. So what it does is that you go to the field and you collect all the data. what I've done is that it gets all your raw images, so you don't get data in JPEG or TIFF or anything, just the camera, the raw format of the camera. So it gets all your data in raw images. It automatically georeferences all your images using the ground control point that you have in the field. And then it creates a points cloud for you. And all of these is in Python, and it's available in my GitHub. It creates a point cloud for you, and then it creates an orthomosaic for you that you can, so there are softwares that does it for you. Agisoft does it, Pix4D does it, but those software, you have to ask your graduate student or undergrad, sit by the software, step 1, step 2, input this, do that. But this one, you just plug in, leave, next day you come back, and you have your output. So it does all these things, creates for you heights, creates for you vegetation indices, and then the amazing thing about it, which I'm very proud, is that it gives you plot level data. And what does that mean for Plant Breeder is that it tells you that, for example, for plot number 4,341, vegetation indices is this, height is this. So you really don't need to go back and look at, okay, which plot is that? Like, what is this? It doesn't give you a pretty image that you can create a magnet and put it on your refrigerator. It's actually Excel sheets of the data that it gives you at the end. So it creates something like this. So for example, OBR means Obregon. It's the city that Summit in Mexico was. So it says Obregon for Viti Yell Trial. So that's very detailed information it gives you at the end. So I validated this and validated this automated method versus hand measurements. And as you can see, the R-score is very high for plant height. And there are, I think I'm running out of time. And this is just like some visualization. Oh, I'm going to show you this video. So this one just shows that the next step that we want to, or I really want to get into, is that we don't really have to use drones only to take images. And then, so the pipeline that I showed you, you take images and then create the orthomosaic. Why not just cut that part, just take videos, and then create the orthomosaic. So this video is what we did is we used DJI. It's the camera that records 4K video. So you just take video instead of taking images and then go to the field. And this is another video if I can play it. So this video goes and as it flies over your field, it can tell you what is the plot number in your field. And this is my last slide. If you let me go, I will go forever, so I'm going to just stop here. Thank you so much.
Atena, hold tight for just a second. Do we have a few questions?
Yes. Yes, please.
So you had a fairly high ground resolution there with your frame extraction using video.
For video, yes.
Yeah. What was your height above ground for your flight then?
This one is 30 meter. It's just because it's RGB, it looks higher resolution than the multispectral one.
But I thought your last slide said you had millimetric ground sample distance.
Which one? Oh, 30 meter is the, oh, did you ask about the resolution or the height of the drone?
Both.
Okay, so the height was 30 meter, the resolution is millimeter, yes.
The resolution is millimeter with an X5 camera from 30, because obviously if you're taking video, you're not getting the full sensor resolution.
Yes, so.
Oh, I'm just yelling.
No, the previous slide was not about the X5 camera.
Okay.
Yeah, so this X5 camera is only about this one that's flying, taking video. Oh, sorry. Okay, so this one you asked?
Yeah, so you have 3.5 millimeter pixel size.
Yes.
And that's at 30 meters altitude?
This one, I'm not sure what was this altitude. No, for our normal altitude that I fly, always is 30 meter, but I'm not sure. If I covered, probably it's 90 centimeter. I can calculate this. Yeah, 30. Yeah.
I'll ask another one then.
Okay.
So your Canada thistle, that looked like a post-harvest detection and identification?
Yes.
So what phenomenology did you use to detect and identify? And could you
We did texture and color.
texture and color?
Yes.
Do you think that would be reproducible under full canopy, full crop canopy around those thistles?
So depending on the crop, because I think texture could be used for Canada thistle, and color depending on the canopy, right? Yeah. The color, but texture I think could be used because the texture was very, to me, very detectable. And then there are other texture analysis that you can use. Or other classification methods, depending on what is your canopy in the field. Yeah.
Atena, I think we'll stop the questions there, so thank you again.
Yeah.
And so we are ready for a break, but before we go, I want to make sure to acknowledge two folks that have been critical to pulling off today. So Heather Coop and Dana D'Amico, both with the center, have helped to pull off this entire event, so you can thank them as you're enjoying your treats. So we'll get together in 15 minutes.